If you're doing a degree in physics, math, or engineering, learning SciPy is essential. Suppose you go through some big, long mathematical derivation and you get a differential equation, for example, and maybe you can't solve it. Well, that's what computers are for, and that's what SciPy allows you to do. Today, we're going to look at things like interpolation of data. We're going to look at fitting data to functions. We're also going to look at things like integration and differentiation. We're going to solve complicated ordinary differential equations that you can't solve by hand. We'll delve into the linear algebra library of SciPy, which can deal with problems that involve very large matrices by using clever techniques to store the data. Finally, we'll look at a little bit of the statistics of SciPy as well, for things like generating random numbers. Suppose you have your own distribution, right? You can put that into the SciPy stats library and generate random variables however you like. Anyways, let's get started. So other than SciPy, I'm going to try to keep the packages as basic as possible today. We have numpy, which is basically used in all Python packages. Matplotlib for a little bit of plotting, and then the main one is SciPy. And now SciPy contains a lot of different libraries itself, and so what I'm going to do throughout the video is I'll be importing different modules from SciPy for different applications. So to start off with this video, I'm just going to go through the basic applications of SciPy. We'll move to some calculus stuff, and then we'll also do some statistics as well. There's a few things that I'm not going over in SciPy, but I'm going over the main things that you should need to know as like a physicist or a mathematician who wants to have all these essential functions. The first thing we'll look at is optimization, and optimization comes up all the time, and it's actually the heart in some ways of machine learning. But optimization, if there's some sort of physical problem, you want to minimize the energy used or something, it's important in all applications. So we'll start really basic. Minimize the function f of x is equal to x minus 3 squared. Now you would know how to do this, using regular calculus techniques, but of course when functions are more complicated, there's not always a technique. So how do we do this? Well, the first thing you do is you define a function, and I'm just going to say it returns x minus 3 squared. So that's our function, which I'm going to call f. Now, in order to get the optimal value of x, I'm going to call the result, res, is equal to minimize. Note that I've imported minimize from scipy.optimize. I'm going to minimize f, and you have to give it an initial guess. So f takes an x, and so I have to give an initial guess to x. And so I'm going to say, well, maybe my initial guess is x equals 2, for example. And so it goes through this. And if I look at the object res, which is this minimize function, it actually contains a lot of information here. So it contains the value of the function. So it says the minimal value of the function is basically equal to 0. It's 5 times 10 to the negative 17. There's some stuff here, but the main thing here at the very end is x, and x is equal to 2.99999. So it's basically found that the minimum is 3, and of course that's sort of obvious just by looking at the function. So if I want to get just that information, I can go res.x, and it returns it in an array, and actually there's a reason for that, and you'll see in future examples why it will return it inside an array. But if you just wanted x, of course, you could take the 0th element of that array to get the value. Next, a little bit more complicated. This is something you probably couldn't do by hand. Now, we're minimizing this two-dimensional function, f of x y is equal to x minus 1 squared plus y minus 2.5 squared. So the function is simple. It's just a basically two-dimensional parabola, but it's subject to these constraints here. And you'll note that every constraint is written so that you're greater than or equal to 0. And whenever you have inequalities like this, you can always write it in terms of something is greater than or equal to 0. So there's a number of lines here that bound it, and then you're also positive. And so you might think, what do all these things mean? There's 5 things here. Well, that essentially means that you're contained in this red little pentagon here. And I drew these beautiful red lines here in paint, so you can see the bound. And so, there's the function here, which is represented by these contours of the 2D parabola. And so you know that the minimum is right here in the center. But the issue is that, you're constrained to this area. And if I told you to find the minimum value, you might want to get as close to possible as that without actually being there. And so there's ways of doing this, right? Maybe the function is even more complicated, and maybe it's somewhere else. But there's ways of dealing with this. So the first thing we need to do is write a two-dimensional function. And And instead of writing it as a function, I'm going to use a lambda function. Remember that a lambda function, it says it takes in the variable x. Now, x is going to be a vector here containing both x and y. Like I know it's written as x and y here, but it's going to take x0, which is the first dimension, minus 1 squared plus x1 minus 2.5 squared. So x has it's like two-dimensional, but the first, thing in that vector is x0, and the second thing is y, which is x1. And so essentially I can give this value f of, suppose I give it two values, 1, 2. This says x is equal to 1, y is equal to 2, and it will return a value here. So that's our function, and we want to minimize this function using SciPy minimize. So the first thing I need to do is I need to define constraints. And there's 5 constraints here. Now, these ones are actually pretty easy. For this, I can just give rectangular bounds. I'll show how to do that. But the main constraints that are tough are the first 3 up here. So let's define these constraints. I'm going to call it CONS. And it's a tuple of dictionaries. It's a little bit complicated of a data type. But I'm going to call it type. And it's an inequality type. The next element in the dictionary is function. And the function is lambda x. Remember, x is the two-dimensional vector here. And it's x minus 2y plus 2 is greater than 0. So I have x0 minus 2 times x1 plus 2. So this says that everything here is greater than 0. Whatever function I give here has to be greater than or equal to 0. And you'll see that here, what I write here. Constraints must be specified as gi of x is greater than or equal to 0. And again, if you're given a line, you can always rearrange an equality such that something is greater than or equal to 0 by adding and subtracting things on both sides. So that's the first constraint, but of course there's multiple constraints, and I can just copy and paste them since it's always of the same form. You always have to give it in this form. The second one is minus x minus 2 times y plus 6 is greater than or equal to 0. And the last one is minus x plus 2 times y plus 2 is greater than or equal to 0. So these are all the 3 constraints here. But I still need to give these bounds. X is greater than 0 and y is greater than 0. And that's really simple. There's also a bounds argument I can take, and I can just say, right, remember, you have to write things in this certain form. Here I have a tuple of dictionaries, right? Remember that. So you can't give it in any old form that you want. It has to be in this specific form. And then the SciPy library says, oh, I know how you've provided me this information. Now I can, interpret it properly. For the bounds, the bound in x is 0, none. None means that it's unbounded. And in y, it's also 0, none. That just says x goes from 0 to infinity, y goes from 0 to infinity. These are the bounds. So that's the hardest part about the problem, is just specifying all these constraints here. Then the problem is easy to solve. It's the same thing, res equals minimize. Remember what I did above here. Here is really simple. Minimize, we're minimizing f. I have to give an initial guess. So I'll give the initial guess as 2, 0. We'll put it right here, and it'll find its way to the minimum value. So my initial guess is 2, 0. By the way, the initial guess doesn't have to be spot on or even very good. Right here, I know I can give it 2, 0. I know that the optimal value is probably going to be somewhere around here, but I'm just going to give it 2, 0, and then it'll show that it will indeed go to the right location. So bounds is bounds, right? This is what I defined here. Defounded. And then my constraints is just equal to CON. So I have the constraints here. It knows to stay in this area. And I have the bounds as well, so it knows that x and y are greater than or equal to 0, which of course are these 2 red lines here. And so I can solve this. Again, I can look at this object that it returns. It actually gives me the value of the function, and it returns the value of x and y. So it says that x is 1.4, y is 1.7. That's the minimal of the function. And the value of the function is 0.8. And again, if I want the value, I go res.x. Now you see why it returns in an array, because if I have a function of multiple variables, it will return it in an array by default. That's why x here, if I solve this problem again, it will return it in an array, because now I have one variable, but oftentimes functions are functions of many, many variables. Now, if I want to look at the documentation of any function, and this is super useful if you're in a notebook, for example, I can go minimize question mark, right? I can enter here, and it will actually tell me all the different ways to minimize functions, all these arguments and options here. it gives me a different method. So there are different methods for minimization. And this is important if you have a problem. Sometimes really weird problems can't be solved with certain techniques, but they can be solved with others. So for example, these are all the names of different techniques for minimization. And some work better than others for certain problems. And of course, here's the bounds that I was talking about. It gives the bounds and the constraints that we used in the last problem. And yeah, so that's just something useful when you're going through a function and you don't quite know how it works. It's good practice to learn how to read this sort of stuff. Now, interpolation will definitely come in handy if you're doing, for example, undergraduate physics labs, or you're in the real world and you're collecting data and you have data points, right? And you want to interpolate what's going on in the middle of those data points. So let me show you something that will help you understand what I'm talking about here. So here I have x and y, and I'm defining it in terms of a function, right? But suppose you're out in the lab and you collect these data points, right? And you say, okay, like I've collected x, y here, x, y here, x, y here. And I say, well, what's going on in the middle? What does the shape of this function actually look like? Well, you can interpolate to get what's going on in between those data points. And now the simplest way of interpolating is just to draw straight lines between these data points, right? And that's sort of a linear interpolation, but it's typically like, you know in your head that that's not really what the function looks like. And so some interpolations are better than others, especially for smooth functions, if you assume that a function is, relatively smooth. So we want to know what the values in between these points are. So I can import this interp1d function here. And so in order to find what's going on here, so notice that I have x and y. If I want to get a function such that I give it any value of x, like I could give it 2.139 or whatever, somewhere in here, it will tell me what the value of y is, right? Just using this data by fitting a smooth curve to it. So I go interp1d, I give it x and y, so it knows to base how it creates the function off the data that I give it. And, for start, I could give it a linear interpolation, right? Let's start with this, and I'll show you what I mean. So this is just drawing straight lines between the points. This is basic and not optimal, but it's good to, for an example here. So now I can create dense arrays of x and y. So I'll go also between 0 and 10. But this time, I'm going to go 100 points. So there's going to be lots of points here. And I'm going to use this interpolation to get me my y points. So it's just f of x dense. So I've created, using these sparse points that are spaced relatively far apart, I've actually created a function that can give me the value at any point. So then I make a really dense, array of x points here, and I have some y points that I can plot. And if I plot x dense, y dense, you'll see that the linear interpolation is just these connected lines in between. But this isn't typically the best way to do interpolations. Typically, you want to use what's known as a cubic interpolation, and that will fit a smoother interpolation to your curve. So I can go kind is equal to cubic. And then you get this function that probably looks a lot closer to what the real function looks like. It's smoother, and you wouldn't expect a function to be jagged like that. If you collected data like this, usually processes in the real world do not have these jagged discontinuities in them. And so you get a function that it rather looks like this. Sometimes you have specific data that you collect in a lab and you want to fit it to a specific functional form, right? So for example, suppose I have this x and y data here and it looks like this. And say I know beforehand, I make an assumption, I say this data is quadratic. Then I want to fit it to a quadratic curve. I don't want to interpolate it. I actually want to fit it to a quadratic curve, y equals ax squared plus b. And the important thing here is that, the reason why I want to fit it to a quadratic curve is because I want to extract a and b, right? Because a and b might tell me something about the physical process that's actually going on here. So it's different than interpolation. Remember, with interpolation, you want to get the values of the points in between, maybe for one reason or another. And actually, there's an example below that I'll show you why you might want to do that. But here, it's more about getting the values of a and b so that you can extract something about a physical process. So for that, I will import this library here. So from SciPy.optimize, import curve fit. Then I need to define this function. So I'll call it func. It takes an x, and it also takes an a and b. A and b are additional parameters. They come after x. And then I just return a x squared plus b. So I have my function defined. Now, in order to get the parameters a and b, this is how you do it. So pop t and pcov. So these are the population, these are like the optimal parameters of a and b for the curve fit. And this has to do with the covariance of the parameters. And I'll talk about what that means in a sec. But I call this curve fit method here that I've imported. I give it the function. I give it my x data and my y data, which of course is plotted here. And I give it an initial guess. Remember, you're seeing a pattern here, right? You always have to give these things initial guesses, because otherwise it doesn't know where to start. So I'll give it the initial guess, p naught is equal to 1, 1. And so we'll go, and in order to get my parameters then, I just look at pop t. And this will give me a and b respectively. Now, p covariance, which is the covariance on the parameters, gives me an estimate of the error on the parameters and also how the parameters are related when you do the fit. So this essentially tells me that a equals 3 and b equals 2 are the optimal parameters for the fit for this quadratic curve here. And of course, when I created the data, I used a equals 3 and b equals 2. So it managed to find the optimal parameters, which of course were how it was created. So this is a pretty simple problem for curve fitting. Now here's a more physics related problem here. So the equation of motion for a spring, right? Suppose you're in the lab, right? And you have a mass on a spring and it goes back and forth and you record it with some sort of sensor and you collect some data, right? You might want to then find what the natural frequency of the spring is, right? And knowing that the equation of motion for a spring is y of t is a cos omega t plus phi, you can fit your data to that curve, and then you can extract the parameter omega, and that tells you something about the physics of the problem. That's sort of what I was talking about before. So you can actually extract particular parameters and then use those to, learn something about the physics of the problem. And then you know something about the spring. So here's the data here. Suppose you collect this data in the lab, and the data sort of looks like this. And so the points here are the actual data points that you might collect in the lab. And then these lines here connect the points. These aren't actual data. I just show them so that you can sort of see the pattern, right? This would be technically a linear interpolation. That's how matplotlib works. It just draws these lines connecting between the points. But the blue are the actual data points. And so you can tell that the data is a little bit noisy, but clearly there's some sort of natural frequency to this, and we can do a curve fit and extract what that natural frequency is. And so noting that omega is 2 pi f, and f is 1 over t, and t is the period. Now, by looking at this plot, you can get a sense of what the period is. And so, seeing that it takes about 2 seconds, right? Looking at this is 2 seconds. And so this is about 2 seconds for a period. I can say t is equal to 2 seconds. So f is equal to 1/2. And so omega, and a good initial guess for omega is just pi. Remember t2, just plug this in here and then plug this in here. And you'll see that omega equals pi is a pretty good guess. Now looking here, you could say, okay, well the amplitude is about 4. And so 4 is probably a good guess for a here, which is the amplitude for y of t. As for phi, well, we're looking at a cosine curve here. You could also write sine, and it would just have a different phi here. But we're looking at cos, and it looks like it kind of starts at its peak. So probably phi is equal to 0 here for this motion. And so then we can fit this to a curve. So now we have 3 different parameters. So it's a little bit more complicated. So same thing as before. It's a function of x, and additional parameters are a, omega, and phi. And it returns a times cosine of omega t plus phi. So that's the easy part. We define the function. And now we want to find the optimal parameters of a, omega, and phi. So for that, I go same thing as before. Pop t cov is equal to curve fit. And I give it the function that I want to optimize. I give it my t data and my y data, which of course is the data that I have up here that I've collected in the lab. and then I give an initial guess for P naught. And I've decided already that a good initial guess was A is 4. Remember that A is the first parameter here, so A is 4, omega is np dot pi, and phi is 0. And there's an issue here, t is not defined, and that is because is x I have to give here. And now I can look at pop t, and it will give me my optimal parameters. So it says that A is about 3.948, omega is about 3, and phi is 0.1. And so now I can plot like what the actual fitted curve looks like. So even though the data is noisy, I fit it to a best fit curve, and I can see what that looks like. So I'm going to make a bunch of values for t. T is np.linspace, 0, 10, 100. You know that the data point goes between 0 and 10, but now I'm going to make 100 values in between. And my y is just the function evaluated at t, a, omega, phi. And that's because I have to go a, omega, phi is equal to this. So now we'll say a is 3.94, omega is this, and phi is 0.1. So now I set my values. I can get these values, and I can plot.scatter my data. So my data is t data, y data. And I can plot my best fit curve. And you can see that my data is represented by these blue points here, and my best fit curve is represented by this curve. So you can see that I probably did a pretty good job at fitting this curve. And so omega is a pretty good guess, right? So if I look at omega, this is a pretty good guess of omega. But of course, there's an error on this, right? It's not going to be the exact value of omega. And I can actually get the error on omega that's contained in the PCOV. This is a matrix. Now, the error on the parameters is given by the main diagonal squared. Now, that's sort of advanced statistics, and the point of this video is more to just talk about SciPy. But this is the covariance matrix, how the parameters are related to each other when you do the fit. And so I can go np.diagonal of pcov, and that will just give me these three values. That gives me the variance on the three parameters. So again, I just get these values. So this is the variance on A, the variance on omega, and the variance on phi when you're doing the fit. And if I want the standard deviation or the error, I just take the square root of this. So take the square root of all the values. This tells me that my error on omega is about 0.004. So it's useful to have this information as well. Again, some people don't necessarily interpret it as error, but it has to do with the variance when you're fitting the parameters. Now, another important thing is that this example really shows why you have to make good initial guesses, right? Suppose instead of guessing omega is equal to pi, I was lazy and I just said, okay, well, I want to have omega equal to 1 as my initial guess. Watch what happens when I fit this curve, right? You see that it actually doesn't find the optimal solution. It will converge to some weird solution here. And so this is a really good example of where you have to have good initial guesses, or the curve fit sort of mechanism won't find the best solution, or won't find the solution that's even the most obvious, because it will probably go in some sort of local minimum when it's in the optimization procedure. So here it's really important that I actually estimated my period and use that to get an initial value of omega. And so again, I'll give it np. Even if I put like 2 times np.pi, if I was off by a factor of 2, it won't find that solution. So I have to be really close to the true solution, and then it will find this curve here. So again, you can't just have a computer do everything for you. You have to sort of look at the data yourself, extract some information, and then do the curve fitting. And so, like I said, the parameters are pop t. These are the a, omega, and phi, and the error on the parameters are the diagonal, well, the square root of the diagonal of p cov. And that gives me my errors on all my parameters. So this is the parameter for a, this is the error on a, omega, omega, and phi, and error on phi. SciPy also has some special functions. So as you go through things like quantum mechanics or electrodynamics or whatever physics course you take, you're going to have these differential equations that have special functions as solutions that are defined as solutions to specific differential equations. So for example, these are the Legendre polynomials, p underscore L of x. They satisfy the following differential equation. If you go through solving for the hydrogen atom in quantum mechanics, you'll get a differential equation that looks like this. And then part of the wave functions of the hydrogen atom come from solutions to this. So this is the angular component of this spherical Schrodinger equation. And L here is an integer. And I was always sort of confused why L was an integer. And the reason for that is because it's non-infinite solutions. So these are normalizable wave functions for the hydrogen atom. So anyways, it's really simple. I just import Legendre. Here I just make some x values. And in order to get this function, notice that I give Legendre 6. That specifies my value for L. So Legendre 6, let me just show this first. So this is my Legendre function. By going into it a little bit more depth, Legendre 6 itself is a function. It's a polynomial function. And if I give it a value of x, it will evaluate that polynomial. There's some other interesting functions too. Laplace's equation shows up in electricity and magnetism courses. And these are functions that satisfy the following differential equation here, where alpha can be any number you want. And so they call them, by definition, capital J alpha of x. And like before, I import this function, jv, that's the Bessel function. And then I can plot it. So unlike before where I gave Legendre 6x, every function is a little bit different, and you probably have to look into that a bit. Here I give it 3, so 3 is the value of alpha, and then comma x is just my array of x values. And I can plot this function, of course, which is a function of x. And this is what my Bessel function looks like. So this is useful, for example, if you're going through something, you get a differential equation, you solve it, rather than having to solve this equation in Python and then plot the solutions, it's just worth noting that SciPy already has these functions cooked up for you. And if you're doing anything where you're plotting the wave functions of different quantum mechanical systems or something, it's useful to keep track of these functions that they exist in SciPy. All right, so moving on to basic calculus functions in SciPy. So in my NumPy tutorial, I already went over like basic things like differentiation and integration. SciPy treats it in a little bit of a different manner than NumPy. NumPy is like about specifically approximating things inside an array and computing derivatives that way from actual numerical data. SciPy, on the other hand, it takes in a function, right? And it will evaluate the derivative itself given a function. So NumPy is give me an array of values and I'll compute the derivative. SciPy is give me a function, right? And I use special techniques to get another function that's the derivative of your function. So it's a slightly different way of thinking, and in some ways, SciPy is better if you have an actual functional form. So for example, here's a function f of x, and now you could differentiate this function by hand, of course. It's a bit of a pain, but it's possible. And for example, I can plot this function. So I define x and then f of x, and this is my function here between 0 and 1. Now if I want the derivative of this function, I've imported this derivative here. All I have to do is derivative f(x) and then dx is equal to 1e negative 6. This is a good separation here. And so what it does is it takes in this function f, it evaluates the derivative at all these points x using dx is really small. So whatever array I give it here, it will evaluate the derivative at all those points given this function f. And you see how easy that is, right? And so I go like this and it will, get an array of these derivatives. Now I don't want all these values on my screen, but I can plot the derivative as well. So here's my function, here's the derivative. And of course, if I want higher order derivatives, all I have to do is go give an extra argument here. N is equal to 2. That gives the second derivative. And I can put any value of n here to get higher and higher order derivatives, of course. So SciPy is really useful for things like integration. And it's slightly different than NumPy, right? In NumPy, you have an array of values. You sum them all up. You use like a Riemann sort of method, and then you get your value for your integral. Now, SciPy is nice because it does all that behind the scenes. And I'll show you what I mean. So the main SciPy integrate function here is quad. So this is my function quad. Now, if I want to evaluate this integral, of course, you could, I don't know if you could do that by hand. It's kind of an annoying function. But all I have to do is, once I import this, I define my integrand. So whenever you're doing SciPy, integrals in SciPy, you define the integrand of the function, which is x squared sine 2x e to the negative x. So I define integrand as a function. So I use a lambda function here, of course, which is just a function. It says, give me x, and I'll return x squared times np.sine of x times this exponential here. And so once I have the integrand and the bounds, right, SciPy will take all that in, it'll eat it up, and then it will spit out the integral using like advanced integration techniques. And so for this, I go integral. And it's even so nice to provide us with an integral error. It's a very kind library here. So integral error is equal to quad. This is, of course, the function that does all the integrating. And I will feed it in the integrand. And then I will feed it in the bounds. And so then it gives me an estimate for my integral here, a 0.102, and the error on this, which is very, very, very small. So it succeeded in taking the integral of this function here. Pretty simple. Now, of course, you can also do double integrals here. And you'll note that my integral over y here actually depends on x. And once again, SciPy has no issue with doing this sort of thing. And the package you would use here is dbl quad, double quad, so double integral. So for this, I again need to specify the integrand. So integrand is equal to lambda. And here it takes in two values, x and y. And it returns np.sine x plus y squared. So that's my integrand. And now I also need the lower and upper bounds on y in the integral. So I'll call this lower y. It again is a lambda function. It takes in x, and it returns a negative x. And the same thing with upper y, except upper y returns x squared. And then, of course, I can do the same thing. Integral error is equal to double quad. So it takes in the integrand, the bounds on the outer bounds on x are 0, 1, and then the lower bounds on y is lower y and lower x. So you note that this function takes in the outer bounds and the inner bounds here are actually functions. So these could also be just numbers, and then I would just return a number in these lambda functions. For example, if this was negative 2 to 2, I would just return negative 2 and 2 here. And so here it will return this double integral. And it's because I need to make sure this is y, and this is also upper y. Remember, it goes from lower y to upper y, and these are functions of x. And I can find my integral and the integral error. So again, very, very small error here. So it's pretty good. I can do the integral of these functions that are, again, this is one of these functions that I don't know if you could actually do by hand. So very useful to have this library here. Now, you can also do up to n-dimensional integrals as well. And that would be from the library, I believe it's called n-quad. And I'm not going to do any examples here. But you can see that if you read the documentation, it tells you how to specify all the different ranges that you go over, right? Because with a integral that's, n arbitrary integrals, right? The bounds can depend on, of course, many of the other variables in the integral. And so you have to read this very carefully to see how to do integrals like that. Now, oftentimes you'll have to solve differential equations that are difficult or impossible to do by hand. And I do this a lot in all the other videos that I have uploaded to my channel, right? And I believe the first video I ever posted was about air friction while falling. And so here, this is what the form of that differential equation looks like. Of course, gravity is contained in beta or alpha. I don't remember exactly. I believe it's beta. And then alpha has to do with air friction, which is proportional to the square velocity. And you might want to solve this differential equation, which you can't solve by hand, but you can do it on a computer pretty easily. And v of 0 says that at time equals 0, your velocity is 0. So you're basically in free fall, dropping from 0 velocity. And for this, there's two different integration or differential equation solvers. There's ODE-int, which I'm going to use for this video. And there's also solve_IVP. And sometimes you have to use one or the other based on the nature of the problem. And so that has to do with more about looking specifically into the problem that you have at hand and seeing which one is better. For example, in my video about the orbit of 3 stars, because that was a chaotic system, I had to use a very specific solver known as DOP853 or DOPE853 in the solve IVP library because ODE-int couldn't handle it. But for most differential equations, the ones we're going to look at today, ODE-int can handle all of them. And they basically work in the same way. So here I'll import ODE-int, and I want to solve this differential equation. So again, all we need to do as the coder is provide all the information about that differential equation, feed it to a SciPy function. SciPy will say, okay, I know everything about the differential equation. I'll crank through, I'll solve it, and then I'll give you the solution that you want. So what's all the information? Well, let's define this differential equation. And so what I need to define is dv dt, right? So any differential equation says, okay, the derivative depends on v and t, right? This is true for any differential equation. If you have like a one-dimensional or first order ODE, you have dy dt, or whatever, in this case it's dv dt, that depends on the variable itself and it depends on time, right? And in this case, it doesn't actually depend on time, but I need to make sure I still have this here because for the SciPy functionality, the function needs to take in 2 variables, and it returns 3 times v squared minus 5. Now, why 3 and 5? Well, okay, v prime is equal to alpha v squared minus beta. I'm just setting alpha equal to 3 and beta equal to 5 as arbitrary parameters here. Maybe you know something else about your particular system, and so I'll just put in these sort of dummy variables. And of course, v naught is equal to 0. So I give my the form of the differential equation, and I give my initial condition. And now I want to solve the differential equation using a SciPy method. Well, first I give an array of times. Suppose I want to solve it between 0 and 1 second. Again, this is sort of dimensionless here, so I'll just call it 1 dimensionless unit 100 times, and then my solution is equal to ODE-int. This is the package that I imported. I give it my dv dt. So this has all the information contained. All the information about the differential equation is contained in this function. I give it my initial condition, and I give it my times. And I have this sol here. And this is sort of contained in a weird format, but again, it will make more sense when you have multi-dimensional or coupled differential equations. And I'll explain that when I get there. But of course here, I only want it as one array. So I can transpose this array to get it as a row like this. And I have to take the first element because you'll see that there's actually 2 axes here. And this will give me my values for the solution. And if I want to plot the solution, I just plot t and sol.t 0. So again, what's going on here? I have solution. In order to turn this into a row vector, I go sol.t. This is the transpose of this array, right? And then I know that there's an outer axis here, so I take the 0th element. And again, it seems sort of weird, and it doesn't really make intuitive sense for one-dimensional differential equations, or single variable differential equations. But as soon as you start having coupled differential equations that we'll look at shortly, then it makes sense why it returns in this format. But anyways, as you can see here, you start at 0 velocity, you get faster, 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 and eventually you reach a terminal velocity. Terminal velocity, of course, which occurs with air friction. Now, this is what I'm talking about with coupled first-order ODEs. So, of course, it only involves the first derivative, but now I have variables y1 and y2. And you can see that the derivative is like y1 derivative depends on y1, y2 as well, and then also x being the dy dx, right? It's the differential equation is with respect to x. And I have an initial condition for y1 and an initial condition for y2. And so how do you solve this coupled differential equation? Well, whenever you have these coupled ODEs in Python, I always define a vector capital S equal to y1, y2. So these are the things that I want to solve for. And we need to write a function that computes ds dx, right? So a function that takes in s, it takes in x, and it returns ds dx, noting that s, of course, is a vector. Now, what is ds dx? Dx dx is dy1 dx, dy2 dx. So, like I said, the function ds dx takes in s and x, and it will make more sense when I write it. So I define my function ds dx. It takes in s and it takes in x. And now, because s is a vector, I know that y1, y2 is equal to s. So I get my components here, and I need to return dy1 dx and dy2 dx. So s is just basically a placeholder variable, but it helps keep things sort of in track in your brain, and it also helps name this function as well. So I return dy1 dx. Now dy1 dx is y1 plus y2 squared plus 3x. So again, I need to return this as a vector. So y1 plus y2 squared plus 3 times x. And the second thing it needs to return is 3 times y1 plus y2 cubed minus cosine of x. So whether it's returning here is dy1 dx, and whether it's returning here is dy2 dx. And because s, of course, is a vector, that's why I named this function ds dx, because it's like it's almost like keeping track in your brain. It's like a vector derivative. It takes in the vector itself and x, and it returns the derivative of that vector, which of course is ds dx. And now I need initial conditions. So my initial conditions here are y1 naught is equal to 0 and y2 naught is equal to 0. And I'll put this inside my vector s, because s contains all the information about the coupled system. So s naught is equal to y1 naught, y2 naught. Again, this is just good practice for writing down everything in a way that organizes it and makes it easier to, go forward with the coding. So here I have this, and now I solve. So x is equal to np.lin space 0, 1. I'll solve it for 100 values between x is equal to 0 to 1. And the solution, like before, is sol is equal to ODE_int function. That's, of course, the differential equation solver that we've imported in SciPy. And it takes in ds dx. It takes in the initial condition s naught. Note that s naught, of course, here is a vector that contains two variables, and I'm going to give it the value of x. And so now solution will make sense, right? And you'll see that there's two things at every time. So it says this array here is that x is equal to 0. And it says that y1 is equal to this and y2 is equal to this. At the next value of x, y1 is equal to this and y2 is equal to this. And this array here is the value of y1 and y2 at the third value of x, right? And so it packages it in a way that's easy to interpret. Now, if I want to get y1 and y2 separately, I need to get sort of this column, and then I could plot y1, and this column allows me to plot y2. So I can transpose the solution, and it will have two arrays here. So this is y2, and this is y1. So if I want y1, I just go sol.t0 is equal to that. And y2 is equal to sol.t1. And of course, there are faster ways of doing this, but this is how I would extract them. And then I can plot the solution. Plot x, y1, plot x, y2. And then this plots the actual solution to this coupled differential equation system. And so, in many of my videos, I have coupled differential equation systems. And it turns out that any second order differential equation can be written as two coupled first order ODEs. And then you would use this sort of methodology to solve those sorts of problems. So this here is an example of solving one of those second order ODEs by splitting it up into two first order differential equations. And SciPy is capable of solving coupled first order differential equations. So the equation for a pendulum is d theta, the second derivative of theta with respect to time, minus it's either g sine theta, I think, but I'll just set g as dimensionless here. Minus sine theta is equal to 0. And suppose I want to solve this in Python. Well, SciPy can only solve first order ODEs. It can't directly solve second order ODEs, but we can transform our second order ODE into a first order differential equation. And so if I define omega as d theta dt, so I'm defining a new variable omega, right? D theta dt. Then I have the following coupled differential equations. D omega dt is equal to sine theta, right? That's by moving sine theta to the other side. And I have the second derivative of theta with respect to time, which is just equal to the first derivative of omega with respect to time. And then d theta dt by definition is equal to omega, right? And so these are two first order coupled ODEs. So I can always define, right, if I have a second order ODE in a variable theta or y or whatever, as long as I define a new variable as the first derivative of that variable that I'm interested in, then I could write that second order ODE as two coupled first order ODEs. And now here I'm going to let s equal to theta omega, right? Remember, s is that vector. I always will talk about s when I talk about these systems. So def ds dt, it takes an s and t. Now in this case, s is theta omega, so I go theta omega is equal to s, and now I need to return. Well, the first component of s is theta, so I know d theta dt is just equal to omega. And the second variable in s is omega. I know that d omega dt is equal to sine theta. So that's ds dt. I'll put my initial angle of the pendulum is equal to mp dot pi over 4. And my initial angular velocity, you'll note that omega is the angular velocity by definition, is equal to 0. So it's starting at an angle of pi over 4, and then it will rotate back and forth. And then my s naught, of course, is just equal to theta naught omega naught. And now I need to actually solve the ODE, get the solution, and then plot what it looks like. So I get my times, mp.linspace. I'll solve it for 0 to 20, 100 values. My solution is equal to ODE int. I give it my ds dt here. My initial condition s naught and my time t. And then theta comma omega, this is the solution, is equal to sol dot t. Right, this last line, if you're confused, remember that sol is just this. Sol dot t is the transpose, so this gives me my thetas, this gives me my omegas. Theta is the first component of s. And then I can extract them like this from this 2D array. And then I can plot them. So plot dot plot. T theta, I'll just plot theta as a function of t, and then I'll show the plot. And you'll note that a curve kind of looks like a sine curve. Well, it's only a sine curve if theta is sufficiently small. Sine theta is approximately equal to theta when theta is really small. And in that case, this is a sine curve. But because we're starting at pi over 4, we're no longer in the small angle approximation. And the solution to this ODE is no longer a sine. It's actually a function that's a little bit more complicated and not solvable by hand. And so this is the solution here. So SciPy can also do things like compute Fourier transforms really quickly. So suppose you have a some sort of time series. You want to get the frequency domain of that time series to find the power at different frequencies. For example, I could play you a note on the guitar, which I've done in my videos as well. You get the time series of the note. But if I convert it to the frequency domain, you could say, well, there's a strong frequency here, and these are the higher order harmonics of that frequency. Well, the discrete Fourier transform of a time series defined as follows, like this, y, which is my Fourier transformed time series, is this sum here, and then x is my time domain, and y would be my frequency domain. And so it's e to the minus 2 pi I, right? That always comes with the Fourier transform. N is the variable that's being summed over, and k divided by capital N is like the frequency. It's like a dimensionless frequency, right? K over N represents a specific dimension frequency, which is dimensionless. Now, if you know what the spacing in x is, right? Because if I just give you values of x for a time series, if you know what the spacing in x is, then you can compute what the dimensions of these frequencies are. And I'll show you an example here. So here I have x and y. These aren't the same. Actually, I'm not going to call these x and y. I'm going to call this t and x, because this makes more sense. Remember, x is our time domain here, and I have some beat frequency looking thing that occurs here, just given by some sine waves and then some random noise as well. So in order to get the Fourier transform of this time series here, first I'm going to define this capital N, and I'll just call the length of x. This is going to be useful. This is the length of the time series. And then my y, which of course is the Fourier transformed thing here. This is just the function FFT of y. And you'll note something, the Fourier transform of x. And you'll note that if I plot y here, so I'm going to plot np.abs y, you'll note that it's symmetric here. Now this is true for any real valued time series. If you take the Fourier transform of a real valued time series, you get this symmetric property. And what's going on here is this is the negative frequency component of that time series. So I can instead just take the positive values by going up to n integer divided by 2. So this gives me only up to half the values here. So I believe it would be here. So these are the positive frequencies, and then it goes over to the negative frequencies. The frequencies, by the way, are given by FFT freq of, you give it the length of the time series, np.diff t0. You might think, well, what is this? Well, this is the delta t of the time series, right? If I go np.diff t, it gives me the difference, right? I have this t, which is a Lin space, and this gives me the difference between all those points in t. Well, it's always the same because we have a time series where the time is always the same, so delta t is constant, right? And so I can get delta t by just taking the first element of this. So this gives me delta t, so you tell it what delta t is, and again, I'm only going to take the first half here. And then I can plot the power at different frequencies. So these are my frequencies f in hertz, and this would be my so-called power at different frequencies. And you see that there's a spike here and a spike here, corresponding to two frequencies, which of course is what I put in. I put a frequency here and a frequency here as well. So now I'm going to go through a little bit more complicated examples here to illustrate the power of SciPy solving more complicated problems in physics. I'm not going to do as much coding, but more just talking about the problem and then giving a quick solution using, the methods we've gone over. So the energy required to get from a point R1 to R2 for a plane, so you have a plane traveling through the air, is given by this formula here that I sort of just came up with. So alpha is a proportionality constant. This says the energy is proportional to the distance the plane travels minus this force that it has to overcome. So you note that this is the work done by a force. The force could be a wind. So if it's windy blowing against it, it will take more energy to travel through that wind. And so we're going to try to find the optimal path a plane should take given a certain wind force coming at it. So suppose alpha is equal to 5. The points are R1 is 0, 0, R2 is 0, 10. So the plane starts here and it's got to get here. Now, on this particular day, the wind produces a force field that's given by this function here. And what you'll note about that function is the wind is really strong directly between the 2 points here. But as you go farther and farther away, the wind becomes less. So the question is, do you battle against the wind and go straight from R1 to R2 in a straight line? Or do you take a curved path and sort of go to where the wind blows less and use less energy? And so we're trying to find the optimal value of A in this path here. Now, if A is equal to 0, then it just goes straight from one point to the other. If A is higher and you sort of plot this vector function as a function of t, it means that the plane is sort of curving out to the side. So the question is, do you take a really big curve? Do you take a smaller curve? Obviously, if you go straight from point A to point B, the wind is going to be too windy. So there's some sort of optimal region. If you go too far, the plane's traveling really far and it's using a lot of energy by going a big distance. So putting everything in here, I evaluate everything I need in these integrals. So I need absolute value of dr dt, and I also need f.dr dt. So I know what x and y are as a function of t. So absolute value of dr dt is given by this square root here. And f.dr, well, I know what f is equal to. And I know f depends on x, but of course x is given by the path of the plane. So this is f dot, and and this should actually say dr dt. This looks messy, but dr dt, like this, is given by this here. So this is f, and this is dr dt, right? Just compute the derivative of dx dt, dy dt, and I get this here. And so this tells me, plugging everything into all the different integrals, I have this function here, and I want to find the value of a that makes it as small as possible. So here we need to combine both integration and optimization. So first of all, I have my function f as a function of a. So f is going to take in a, and it will return how much energy the plane uses. And so this is the energy here. So the integrand here, I just defined the integrand is everything in here. There's nothing too confusing there. And it returns the integral of the integrand from 0 to 10 dt. That's how much energy the plane uses. So the first step is that I define a function, takes an a, it does this big complicated integral, and it returns the value of the integral. And then I use the minimize function with an initial guess for a and a particular method. I don't even think I need to specify the method here. And it will return for me the optimal value of a. So if I run this, you'll see that the optimal value for a is 1.426. So a is 0, is going straight. So there actually is a curvature that you need to take, and it gives me the optimal value here. So here we've combined both integration in SciPy, but also optimization, and that comes up a lot in various problems. Typically, when you're optimizing something, it's a complicated function. It's not just like optimize x minus 3 squared. It's, a function takes in a parameter, it does a bunch of stuff to that parameter, it might solve an integral, and then you get a value for that integral, and you want to make that integral as small as possible. So this is a complicated integral that you couldn't really solve by hand, but you can optimize for in SciPy. Now, here's another thing where things become sort of coupled together. Here we have a differential equation, and we're going to here combine differential equations and then also interpolation, and I'll explain what I mean. So Newton's law of cooling is given by this here. You've probably done this in a first year course. dt, T is temperature, little t is time, and K is a proportionality factor. T is the temperature of some sort of body, and Ts is the temperature of your surroundings, right? And typically the temperature of the surroundings is constant, but here I'm saying the temperature of the surroundings depends on time. And that's like, if you're out about during the day, the temperature of outside gets warmer in the middle of the day and colder at night. And so the problem here is T represents the temperature of a shallow pool, and Ts of T represents the temperature of outside. And then, so suppose you collect some data from the temperature of outside. What is the temperature of the pool? So this is some times and some temperatures. So I can plot this. So this is the temperature as a function of time throughout the day. And I put the temperature in Kelvin. I didn't want to choose degrees Celsius or Fahrenheit because I know I have lots of viewers from America and I don't want to make them mad. So Kelvin is the physics unit I'll be using here. And it goes from 282.5, which by the way is 10 degrees Celsius, the better unit, up to 302 degrees Kelvin, and then back down to about 10 degrees Celsius. And I think this is like 30 degrees Celsius. Remember, degrees Celsius is the better unit here. And so here's your temperature throughout the day. And of course, this is Ts of T, but of course you need a function here. If you're solving a differential equation, you can't just have these data points. You need a function that gives you Ts of T. And so the first thing to do is to make an interpolation function. So Ts will, I'll use this interpolation function that's from the earlier in the video. I give it the times and the temperatures. And then what I can do is I can give it any value of time that I want. For example, note that this is in hours as well, from 0 to 24 hours. I can say, okay, now I want it at 1.345, some number here, and it will give me the Ts like that. And so this is really useful. So I've collected some data. Now I have Ts of T. I know explicitly the functional form of this because the functional form is simply an interpolation. And I can take in any value and it can spit out any value. That's the definition of a function. So I have Ts as a function of T. Now I need to solve the differential equation. So I have dt dt, which is of course a function of t and little t. This is a one-dimensional ODE. So like before the examples I went over, I define everything I need to know about the differential equation. I find the times that I want to solve it for. So it's t minus Ts of t. Remember that Ts is a function here. It takes in a little value of t, and it will return what the outside temperature is throughout the day as a function of T. And I'm going to set my, I'm going to go from 1 to 23 hours, so from here to here. And I'm assuming that the initial temperature of the pool is about this temperature. Maybe you measure the temperature of the pool at the beginning of the day. So my initial temperature of the pool, I can get the solution. Of course, there's an error here. And that is because I need to plot times and the solution. And you can see that these red points are the outside temperature, and the blue is the shallow pool, right? So T is some shallow pool that you're putting outside. I think I mentioned that. And you can see that there's a bit of a delay. And this is like if you're swimming in a lake too, right? The hottest part of the lake, or the surface of the lake, is usually what heats up. It doesn't correspond to the hottest part of the day. There's a bit of a time lag here. And so although the hottest part of the day might be at noon, the lake has a bit of a time lag, and then the hottest part will be maybe, 2 or 3 o'clock for the heating there, and then it slowly cools off. And so this is an example of where you collect data, you use it to get information on a function that shows up in a differential equation. Then using interpolation, you can solve the differential equation. So note what I've done with these two examples is I've paired things. Here I've paired integration and optimization, typically show up together. And here I've paired ODE solving and interpolation. Again, things that typically show up together. Now I TA'd for a second year course. One of the questions they had on one of their assignments was, you have a system of a star with all these chemical reactions that take place. And chemical reactions depend on temperature of the star, right? If the star's hotter, they go quicker. And so they had about 8 coupled differential equations that depended on the temperature. And he gave a time series. He said, okay, we look at through our telescopes and we determine the temperature of the star as a function of time. Then he gave the data and they interpolated that data to get a function for temperature, sort of like what we did here. And then they solved a bunch of coupled differential equations as a function of time after already having interpolated that data. That's a really tough problem, but it's like the ultimate problem solving with these SciPy methods here. Okay, so there's a lot of linear algebra that can be done in numpy. SciPy is about making it as efficient as possible. So I'll just go over some cases here where if you had really large matrices, you'd probably want to use these methods. So for triangular matrices, if you want to solve an equation that looks like this, right? AX equals B. This is triangular because there's 0 values above the main diagonal. It's a lower triangular matrix. These show up in certain kinds of problems. So here I go, I import the solve triangular. I define A, which is the matrix. I define B, which is this vector here. And if I want to get X, I go X is equal to solve triangular A, B, and it's a lower triangular matrix. So I give lower equals true. And I can find X, and it will give me the solution to X. Toeplitz matrices, they show up a lot. They show up in some of my videos that I made. These are matrices with constant diagonals. For example, if you were to represent the 2-dimensional Schrodinger infinite square well, right? Then technically, if you were solving it using a linear algebra method, you would have a Toeplitz matrix. Now, that's not obvious why that's the case unless I go through it. But in fact, I'll go through it a little bit below in this video. But anyways, these are matrices with constant diagonals. And how do I solve this? Well, it turns out if I specify the first column of T, 1, 3, 6, 10, and the first row of T, which is R, 1, negative 1, 2, 3, then you know everything else about the matrix. So a Toeplitz matrix can be specified uniquely by the first column and the first row, and then it can automatically know what everything else is. So here I define C and R as the first column and the first row, and B is the vector here. And here I would go X is equal to solve Toeplitz. And I give it CR and a tuple like that, and then B. And then I can find what X is. And it will give me the solution here. So again, these are matrices that show up. If you want to do the optimal way for solving these things, if you have really large matrices, you would typically use these methods here. Now again, I showed how to solve eigenvalue problems in NumPy, but here I'll focus on a particular case. For example, tridiagonal matrices, they show up a lot in eigenvalue problems, especially for differential equations. Again, they show up all the time in videos that I make on any sort of quantum mechanical system where you're trying to find, like, for example, a good example of this is the one-dimensional square well with an arbitrary potential. You get this tridiagonal matrix. Now, you note that this matrix is both tridiagonal and toplets because it has constant diagonals. And it's only the main diagonal, one below, and then one above. That's a tridiagonal matrix. And so to solve this problem, I would first specify the main diagonal, which is just 3, 4. So it's 3 times 4 ones, right? So this gives me an array of 4 ones multiplied by 3. The off diagonal is equal to -1 times np.1's 3. And I can get my eigenvalues and my eigenvectors. It's just tridiagonal d comma e. And of course, I have not imported it. And so this is my eigenvalues, and my eigenvectors are returned in that weird way, sort of like how they're returned in numpy. So I need to take the transpose of this matrix here that it returns. And if I want to get my first eigenvector, that's vt0. So this is my first eigenvector. My second eigenvector is the transpose 1 and 2, 3. It's sort of a weird way that they return it, but it's sort of the default way that they do that. And we can check that these are indeed the eigenvectors by going A. Well, first let's make a matrix A. So if I want to make this matrix, by the way, a really easy way to do this is A is equal to np.diag d plus np.diagonal. So this gives you a matrix where there's only one diagonal and it's filled with this vector here. And here I'm giving it E and I'm saying I want you to put it one above the main diagonal. And here I'm having another matrix here, one below the main diagonal. So for example, I'll show you what I mean. If I go np.diag d, it puts 3's on the main diagonal. If I go np.diag e, it will take this thing here, this vector, and put it one above the main diagonal. And then I can add these all together to get A. And I can check the eigenvectors are indeed the right ones. A at vt1 should be equal to, by definition for the eigenvalue problem, omega 1 times vt1. And I indeed get the same result, meaning that omega 1 is indeed an eigenvalue of A for this particular vector. There's also ways to construct special matrices. So here's a Feidler matrix given like this, where AI minus ij, where AI is some sequence of numbers. You know, these might show up somewhere. I haven't actually seen them show up, but again, this is just exposing the functionality. So 1, 4, 12, 45. This might be the sequence AI, right? AI is the sequence of numbers, and it constructs this matrix here, right? Pretty simple. Also with toplets matrices, toplets, these are the ones with the constant diagonals, remember? And like before, I only have to give it the first row and the first column, and it can construct the matrix, knowing all that information. And of course, there's a link here to a bunch of other special matrices as well. There's also matrix decomposition. Sometimes you want to take your matrix, convert it into the product of other matrices. So this is LU decomposition. Can't say that apparently. So here I go A, let's define our arbitrary matrix, np.array. I'll give it 2, 5, 7, 8. Sorry, I shouldn't have deleted this. 2, 2, 8, 7, 5, 6, 6, 5, 4, 4, 8. So this is just some random matrix A. I also need to put outer brackets around it. I can look at this. And here it will convert it into P, L, and U, where P is a permutation matrix, L is lower triangular, and U is upper triangular. So I just, really simple, P, L, U is equal to LU of A. And it returns 3 matrices. The permutation matrix, which of course is all 1s and 0s, lower triangular, and upper triangular. That again, that might be useful for a particular application. Cholesky decomposition, I had to use this recently in my research actually. It's finding a matrix C such that A is C, C, T. This had to do with autocorrelation of sequences, but again, it can be used here as well. It's just a matrix problem. It says find a matrix C such that A your matrix A that you specify is equal to C times C transpose. So I have to specify A. And here I'll just give it a simple 1, 0.2, 0.2, 1. So this is my matrix. Again, I need to make sure that I put outer brackets around here. This is my matrix A. And if I want to find the matrix C that satisfies this equation, I just go C is equal to Cholesky A. And now there's typically two different matrices that satisfy this. I want the lower triangular version. And then C, that matrix here. Now, what I've used in many of my videos are sparse matrices. And these come in handy when you have really, really big matrices that your computer can't actually store because there's too many variables. But because there's so many zeros in these matrices, right, you don't need to store all that information. That's what sparse matrices mean, is matrices that contain lots of zeros, so lots of space can be reduced. And I want to give a useful example here that has to do with my videos. I encourage you to watch my one-dimensional Schrodinger equation video and my two-dimensional Schrodinger equation video. But I'll go over this example here. So the second derivative of a function f, f of xi, which I'll specify as fi, so you have a bunch of discrete points as your function, can be approximated like this. D squared fi dx squared is equal to this, right? Suppose I have f0 to f4, right? These are just 4 functional points, right? And I know that f0 and f4 are 0. So I have 1, 2, 3. It's just a really discretized version of it was a continuous function, but I'm just saying 3 points in the middle. Well, the second derivative is approximated as, well, I can put my values of f of my function into a vector. f1, f2, f3. I know that f0 and f4 are 0. The second derivative is represented by a matrix D, where D is equal to this here. Again, you'll note that D is tridiagonal. You'll also note that D is toplets. So you see where these matrices come up. Again, take the matrix multiplication, D times F, and you'll find that each entry here will be the second derivative. Right? Minus 2 times F1 plus 1 times F2. Divided by delta x squared. This is exactly this expression when f0 is equal to 0. So again, try this out, do it by hand, and you'll realize, this matrix does represent the second derivative. Now, this works for like one-dimensional functions, right? If I'm solving the one-dimensional Schrodinger equation. In 2D, however, our function is specified on a grid, right? And so our function might look like this with a 0 boundary condition on the outside, and then these are the values of our function in the middle, right? But when you're doing this sort of work where you're computing second derivatives like this, it's better to store this information as a vector. So I can convert this matrix here into the following vector. I just take the first row here, I put it like this. I take the second row here, I put it like this. So now all my information, I've stretched it out into a vector. The question is, what does the 2D Laplacian look like, right? Del squared, second derivative, vector derivative. It turns out it's equal to the Kronecker sum of our original matrix, right? And so the Kronecker sum I write is this symbol here, D plus D. It's a really big matrix, right? It's n squared, right? Because this is a 3, so the vector goes to 9. If this were like 10, this vector would be 100 big. If it were 100 by 100, right? This would be 10,000 long. And so this matrix here would be 10,000 by 10,000. Too big to store on a computer at that point when you have floating point numbers, where D is equal to this. So the Kronecker sum takes an n by n matrix and converts it into an n squared by n squared much bigger matrix. So if D is 3 by 3, D plus D is 9 by 9. And I encourage you to look specifically at the mathematics if you're interested in what the Kronecker sum is. So here's a simple way to take the Kronecker product of a matrix. So suppose I have a 5 by 5, length 5 vector. Well, I'll give my diagonal here. And my off diagonal. This is, again, I'm constructing a Toeplitz matrix here. And then my diagonal matrix D is equal to np.diag D diag E k equals 1. This is assuming, by the way, that delta x is equal to 1. And then I have my matrix D that I was talking about. So this is a 5 by 5, basically this matrix here, but 5 by 5, right? There's a simple function they have with the Kronecker sum. The Kron sum is equal to Kron, right? So I'm importing the Kronecker product here. Now, this is the Kronecker product, not the sum, and I want the sum. And the sum is actually defined in terms of the product. So for that, I need this here. So it's the Kronecker product of D with the identity matrix plus the Kronecker product of the identity matrix with D. That's how the Kronecker sum is defined. I know it's confusing here, like it's called Kronecker product, and then we compute the Kronecker sum like this. And then I have my D Kron sum. And you note that even though the D was 5 by 5, D Kron sum becomes 25 by 25, so it becomes like a much, much bigger matrix. Now you can imagine what would happen if n is equal to 100. It's too big, too much information. This is where you need sparse matrices. So here I import the sparse module of SciPy. And now I could say, well, maybe I want 100 by 100. Again, it's the same thing. I'll define a diagonal. np.1's n. And my diagonals, my array are diag minus 2 times diag, like that. And then I can construct my diagonal matrix. Is this SciPy sparse? So this, again, gives my diagonals of my matrix. And so I use sparse.spdiags. I give it my diagonals. I say I want them on the following points here. So this is below the main diagonal is -1. 0 is on the main diagonal, and 1 is 1 above from the main diagonal, like that. And n. And this will get my matrix D. It's a sparse matrix, 100 by 100. It's this matrix here, and if I want the Kronecker sum, I just go sparse.kron sum of D with D. So I'm taking the Kronecker sum of D with D, and now it's a 10,000 by 10,000 sparse matrix. And again, watch my 2D Schrodinger equation video. I go over this in depth as well, of why you would do it this way. And this is, for example, how you would solve the 2D infinite square well, but with an arbitrary potential in the center. So you can do pretty cool things with these sparse matrices, and you need sparse matrices to solve those problems because it's very difficult to do so. Otherwise, you just run out of memory with the computer because the matrix is too big. You'll know that even though this is 10,000 by 10,000, there's only 49 or 50,000 elements actually stored in that matrix. That's why it's sparse. Lots of zeros in that matrix. Finally, we'll look at doing some simple statistics in SciPy. So, of course, with statistics, you have distributions. Those distributions will have mean values, variances, all sorts of properties from them. And then probably most importantly, if you're doing any sort of simulation, you might have a specific distribution that you want to actually draw random numbers from. For example, you might have a normal distribution that you draw normal random numbers from, or a beta distribution, or whatever distribution you want. Maybe you have your own custom distribution and you want to draw random numbers from that distribution. That's a very important thing. But there's also, of course, the functional form of the PDF, the cumulative distribution function, which is the integral of the probability density function. These things are so important, especially for things like quantum mechanics, where these distributions show up all the time. So here's a beta distribution. Gamma here is the gamma function, right? And so the beta distribution looks kind of like that. So I can import everything I need from beta, and it returns this nice functional form. You don't have to code this up yourself. It can actually return the PDF here. So this is, of course, the PDF. X goes between 0 and 1. It's a very particular PDF. So, for example, I can choose values for A and B. I can say A, B is equal to 2.5, 3.1. And I can plot the probability distribution. Well, I can get basic statistics first, actually. If I want the mean, the variance, the skewness, and the kurtosis, I can go beta.stats. So note that beta is this whole library. I just go beta.stats. I give it the values of A and B. And I specify which moments that I want. And I want the mean, variance, skewness, and kurtosis, right? So mean, variance, skewness, kurtosis. And it knows to return 4 things, right? And then I know exactly what my mean value is for that, what the variance is for the distribution. So it's very easy to get statistics from a distribution very quickly with SciPy. A lot of times, maybe that's all you need. Now, there's also plotting the probability distribution. So let's make some values between 0 and 1. 0. Well, okay, so I could go 0 and 1 because I know explicitly that we're between 0 and 1 here. But there's a better way to do this when you're dealing with these PDFs, right? And so what I can do is I can say beta.ppf. And I can go question mark here just to show you what this is. This is the percent point function. It's the inverse of the CDF. And you're probably thinking, why do I want the inverse of the CDF? Well, it's kind of nice because I can give it a value. I can say 0.01, and then I give it my values of A and B. Remember, A and B are just the values of the distribution. If you were to plot the PDF, it gives me the x value such that the integral from 0 to that value is 0.01%, and the x value here is 0.7. Now I know it goes from 0 to 1, so if I say like 99%, right, it should be pretty close to 1, right? Because the CDF will go to 1 when x is equal to 1. So 99% of the area of the PDF corresponds to this x value. And now for these like distributions where 0 goes from x to 1, right, I could just go 0 to 1. But for example, when you have the Gaussian distribution, right, you want to plot the Gaussian curve, that goes from negative infinity to infinity. And you're not going to plot it all the way out from negative infinity to infinity. So you can decide like how much of the area you want to include in your plot like this. So here, for example, I would say maybe I just want to plot from, this small value of x to, didn't mean to do that, to this large value of x that constitutes 99%. And I'll go 100 values. And then I can plot x, and I'll choose the beta.pdf xab. And note that it doesn't quite go from 0 to 1. Now, in this particular case, and this is dangerous when you have infinite distributions, I could say just 0 to 1, right? Just give me 0 to 1, exactly. If I were to plot the normal distribution, 0 to 1, remember that 0 corresponds to negative infinity and 1 corresponds to positive infinity, so you'd get nan numbers and you couldn't do it. So this is a particular case where you can do it this way. The Gaussian distribution, of course, you have to be a little bit more careful. Again, it's the same thing. I can say mu is equal to 1, sigma equals 2, and I can extract the mean and the variance of this distribution. Remember, for the normal, mu and sigma basically tell you the mean and standard deviation. It's one of those distributions where you can literally look at the parameters and find the mean and standard deviation. So maybe this is a little bit counterintuitive, but norm.stats. And so this is the... Technically, this is the normal distribution with mean of 0 and standard deviation 1. But you could specify location and scale parameters. Remember, the Gaussian distribution with mu and sigma is just a scaled version of the normal distribution, and it's also shifted by a value of mu. This is local is equal mu. That's location. Remember, mu specifies the location of where it's located, and scale is equal to sigma. These are location and scale families if you ever look into statistics more. And I just want the moments as mean and variance, right? And I need to import it. And I can look at mean and variance, for example. Mean is 1, just like I expected. Variance should be 4. Standard deviation is 2. Variance is 4. So like before, we can plot this distribution. So I just basically copy this and make sure everything is adjusted. So beta goes to norm. Beta goes to norm here. Beta goes to norm. And I replace A and B with mu and sigma. And this just is how I replace all 3 of them. And of course, it'll throw the error here. So here I'm going 0 to 1, but that corresponds to negative infinity and infinity, and linspace just won't deal with that. So I need to make sure I give proper bounds here. And then I have my normal distribution, right? And this constitutes, I guess, from 0.01 to 0.99. That would be 98% of the area, right? Because 1% of the area is to the right here and 1% of the area is to the left there. And so that's how you use this PPF function to plot things properly. PPF is useful, the inverse of the cumulative distribution function, because it gets you particular values that correspond to less than a certain CDF. Now, there are also distributions that have many variables, right? We looked at these are sort of 1D distributions. They only have x as their variable. Here we can have x1 to xk. This is the multinomial distribution, for example. But of course, there's also many other multivariant distributions in the world as well for different reasons. So here's multinomial. I have x1 to xk as my variables, right? And then the probability of each one of these things. x1 to xk are numbers, right? So it says like, what's the probability of getting, 2 x1s, 3 x2s, right? For example, if you have a dice and there's 6 different sides you could roll, x1 would be one side of the dice, x2 another side of the dice, and it's saying what's the probability of getting a certain number of 1s, a certain number of 2s, a certain number of 3s. So multinomial, right? Here I have to specify my probabilities. So if it's a dice, I have 6 probabilities. All of them are equal to 1/6. So for example, P is equal to np.16 divided by 6. Right? See how quick that is, right? You just, an array of 6 ones and you divide them all by 6 and you get a bunch of 1/6. And then I can go multinomial dot PMF. This is the probability mass function, like the probability density function. And I can say, well, what's the probability of getting, for example, 6 ones and 0 of everything else, given that n equals 6. So this is I roll the dice 6 times. There's equal probability of each roll accounting. What's the probability that I roll 1 6 times in a row? Very, very low, right? So this can be used to evaluate specific things. And I can also generate multinomial random numbers as well. So for example, suppose I do 100 trials. Probability is P. And I roll, size equals 5. So let's talk about what this means. So this says, of course, I have my, I do 100 rolls, right? And there's 6 different options, each with a probability of 1/6. And so this says I do 100 rolls of the dice, and this will generate a random thing. So it says I rolled 1 19 times, I rolled 2 17 times, 3 18 times, 4 is 20 times, for example. And there's 5 trials that I do. So I roll 100 dice once, and then my next trial I roll 100 dice again, and then I get 22 ones, 12 2s, 23s, 12 4s, etc. And I do this 5 times. So there's a lot of number here. There's n equals 100, size equals 5. There's 6 different options. You have to keep track of this when you're dealing with the multinomial distribution. Now, finally, you might want to generate random numbers from your own distribution. So again, this is a distribution from my research I was working on recently. It doesn't have a name, but I'll call it P-solver distribution just because. It wasn't invented by me, but that's the way things go. Unfortunately, you can name something and steal things, and it's all good. So here's a distribution here, f of x, and the parameters are a1, a2, b1, b2. And the distribution looks like this, and it's 2 decaying exponentials with the square root of x. 0 goes to x to infinity. So if I wanted to define my own distribution, right, I would import scipy.stats as st. This is a SciPy stats library. And here you have to do a little bit of object-oriented programming. So I inherit from this strv continuous class, and then I redefine the PDF here. So here I'm making my own distribution that inherits from this sort of general class of all distributions in SciPy. And I define the PDF of x, a1, a1, a2, all the numbers here, and it's equal to this function. I basically just input this function. And then I say my random variable is my p-solver distribution, which is essentially this here. and I'm saying a equals 0, b equals infinity. That's not these a's and b's. That corresponds to the bounds 0 and infinity here. So that's what those mean. Then I have my random variable, right? And now I can generate, well, first let's plot the PDF. So here I give some values of a1, a2, b1, b2 from this here. I make an array of x. And here I'm doing the same thing as before. I use this ppf function to get the 0.01 and the 0.99, right? Remember, it goes out to infinity. So 99%, it won't go out, infinitely far. 100 values. So this says go from this value to, this will be close to 0, to this value. This might be very large. 99% of the PDF is contained up to that point. 100 values. And y, here I'm just plotting the PDF. So I have my random variable, which is an instance of this class. And I'm giving it the values of x and a, and I can plot it. So here I plot it here. And I use a logarithmic y-axis here. And this is what the distribution looks like. This models, if you're curious, it was used to model pileup, in other words, noise in the Atlas detector. So there's, whenever you have collisions and you have a particular cell that's detecting things, there's sort of noise that goes into it. And this is one of the distributions you can use to model the energy going into that cell of noise. And so I can also generate random variables, right? So here's 10. But if I want to generate 100 of them, right, it takes a while. So even though I define my own distribution here, I can generate random numbers, but it typically takes a little while, right? So 500, not very many. And it's using the PDF that I've defined here, and it generates them pretty slowly, right? This is taking quite a while for 500. But there are ways that you can define your own random variable generator, right? Random number generator using this distribution. So here I define the PDF of my distribution. I also define the CDF, which is just the integral of the PDF. There's a closed form solution. You can integrate this function. There's a solution to that. And here I don't want to sort of talk about exactly what I'm doing because it's sort of statistical in nature. But here I define my own method, _RVS, for generating random variables here. And then, right, I can make a new instance of my class. So I redefine my class here with a new random variable generator. And I can make a new instance of my class, and then I can generate, say, 10,000 random variables. And I run this, and it does it instantly. Remember, 500 took a while before. Now I'm generating 10,000, and it does it basically instantly. And the reason for that is because I use a faster way of generating random numbers here, using an approximation method sort of thing. So anyways, there is other things in SciPy as well. There's image processing, which is a huge part of SciPy that I haven't really gone into here. And the linear algebra library has tons more stuff too. But I hope this gives you a good foundation so that you're confident to solve theoretical physics problems, things like, you have a differential equation that shows up all the time. You do a bunch of physics, you get a differential equation, and you actually now have the ability to solve and plot it. That's a huge thing. Interpolating data from experimental physics that you collect in the lab. That's another important thing to, look at the physics of that problem. And then things like integrating and taking derivatives and stuff that's important as well. Anyways, if you like this video, please like the video. Please subscribe to my channel and check out my other videos because all my other videos use the stuff in this video. And it's cool to see that stuff applied to more complicated problems. Anyways, thank you guys, and I'll see you next time.